Hey, you're 13. How's it going? It says over there, there's Dixon. Is Wingkit last in the room? No way. Where's Wingkit? Wingkit! Ha! Okay, folks. Right. No way. Okay, my sound works. I keep, by the way, Julian, I keep checking the sound now at the start of each lesson because I've been issues. Right. I'll mark Wingkit as absent until he arrives. And we can move on. Let's crack on, folks. I don't want to waste any time. Okay, so we've been working through A2 kinetics. I set you guys a homework of kinetics 2. There he is. Hey, Winkit. Good to see you, dude. Our learning objectives for today's lesson. Oh, I feel like I want to make that bigger. Learning objectives for today's lesson, folks. I haven't shared my screen with you guys, have I? Hang on. Share my screen with you guys. Go, go, go. Share. And we're in. I like it. I'll get rid of my keyboard. Gonna bust that eventually. I snapped the tip off my pen today. This is what happens when you use this like all the time. It's getting battered. Right. Okay, folks. So now that I've gone and created that box, I'm just gonna write underneath it. Learning objectives. We need to work. Okay, that's a bit thick. So understand mechanism, affects rate equation. You guys seeing okay? Is everything all functioning? Understand, it's not a good sign. Understand RDS. Now, RDS stands for rate determining effect. Rate determining effect. I like it. The last learning objective that I put onto YouTube was be able to use rate equation, be able to use the rate equation to predict slow step. I'll put RDS. That seems reasonable. I'm sorry about the learning objectives being so long, guys. I really do. I do apologize for that one. Obviously, the first thing I need to do is I need to go through the homework that I set you guys. So insert printout. You guys were working on kinetics 2, which is there. Oh, sorry, we couldn't add your printout. Oh, that's odd. Documents, year 13 worksheets. Where's kinetics 2? There it is. Okay, I'll download it. Oh, it's a Word document. That's why my tablet doesn't like it. Don't like it. No like it. No like it. Download. No. Do I want to download this? No, because it's going to... Oh, download as a PDF. Nice. Documents, year 13. Let's do it here. I like it. A2. Sorry, guys. I thought this was all set up and ready. Kinetics, HW, right. Okay. Now I can insert it. Insert print at documents, year 13. Come on. Kinetics 2. Right, so this was just, it won't take me very long, folks. Only 6 marks. Just want to go through it, and then you can add. I've got a document which I think is tracking your marks, right? I made an A2 one that you guys have been filling out. So you guys can add your results there. Okay, let's be really quick. It says determine a value, rate equation, calculate constant and its units. Okay, so question number 1. These all should be pretty quick now. We're starting to get used to this. Yeah, we've just got to watch out for those tables when they're being flipped. That often drives me crackers. Stays the same. Oh, I'm going to make my pen thinner. I'm also going to do it in red. I think that seems very reasonable. Stays the same. Yeah, times by 2. Rate times by 4. B is second order. Should be nice and easy by now, folks. Should be getting used to this. Next one. Stays the same. Like it. Stays the same. Times by 2. times by 2. So A is first. Rate equals K. A to the power of 1, B to the power of 2. I like it. Right, let's calculate our rate then, our rate constant from this. Reorganize the equation. Rate divided by A to the power of 1 and B to the power of 2 gives me K. Input my numbers, choose a string. I'll give it the middle one just for fun. Yeah, middle one. So the initial rate was 8 over 1 times by 2 to the power of 2. I like it. 8. So 1 time, so I can just make that vanish. 8 divided by 2 to the power of 2, 2 squared. Gives me a rate constant of 2. And my units, moles per dm cubed, moles per dm cubed, bring it up. It means moles to the minus 1, dm to the plus 3, s to the minus 1, and I'm done. Can someone check me, please? Winkett, Julian, Dixon, did I get it right for number 1, please? Next. Stays the same. Times by 2. This isn't complicated. No effect. So D is 0. Next, I need D's never kept the same, but it's 0 order. It doesn't matter. Great job. Thank you, Winkett. Sounds right, Dixon. You should have done this. You're meant to be marking your own work, Dixon. So you haven't done the homework, have you, Dixon? You're lying to me. You haven't done your homework. Come on, Dixon. You've fallen right into that trap. Right? So it doesn't matter. I am. Sounds like I am. What? I have proof. Oh, okay. Well, did you get 2, Dixon? That's what my question is. So that's times by 4, but it's to 0 order, so it doesn't make any difference. We've got to do stepping now. Yeah, times by 4, but to 0 order, which means it stays exactly the same. Right, that's a times by 4. What did I do there? Times by 4. E is first order. Yeah, rate equals K e to the power of 1, and we're done. Right, reorganize. Rate divided by e to the power of 1 gives me e to the power of 1, gives me K. Choose a string. I choose U. That was terrible. I choose U. Right, so I'm going to choose rate. Rate of 0.2 over e to the power of 1, which is 1. So the answer for K is 0.2. Units, moles per dm cubed, moles per dm cubed, it's s to the minus 1, and I'm done. Guys, did you get 0.2 s to the minus 1? If you did, great job. Please let me know if I'm correct. I'm as fallible as the next person. I'm going quicker than I normally would. Please try and be on it for me, guys. Right, next one. Oh, stays the same. Times by 2. Right, guys, this is much more realistic. This is much more realistic data. Yeah, Julian, great job. Thank you. So that's a times by 2. Yeah, you realize that there's always idiosyncrasies with chemistry. You're never going to get an exact times by 2 on the rate. It's going to be slightly off. That's perfect. This is much more real data. Yeah, so P is first order. My pen is having a slight issue here. It's because I snapped my pen and I'm now just using a stick essentially in my thing, and it's not going well. Next, right, P never stays the same. Let's compare these guys. Oh, that's an interesting change, isn't it? 0.4 divided by 0.3. That's a times by 1.33, right? So this would have gone up as first order times 1.33. So 0.00603 times by 1.33 gives me an answer of 8 times 10 to the minus 3. Right. Oh, interesting. Shift eng. Okay, 0.008 makes it easier for me to see that. Just going to try. I just did shift eng on my calculator twice, and it gives me 0.008. That makes them so much easier. So that there is a times by 2. Much more realistic numbers. What did I do there? Times by 2. Q's first order as well. Right. Rate equals K. P first order, Q first order. I like it. Reorganize. Rate over P, Q first equals K. Choose a string. Number 2. I'm going to go 0.00398 divided by Q, P of 0.2 to the power of 1 times by 0.1 to the power of 1. Right. So I'm going to do it just becomes 0.2 times 0.1. 0.00398 divided by brackets 0.2 times by 0.1 gives me an answer of 0.199. Well, sorry, that rounds 3 sig fig of that. Yeah, and what are my units? Moles per dm cubed, moles per dm cubed. Bring that one up. Moles to the -1, dm to the +3, s to the -1, and I'm done. Tell me if I got it right, folks. Did you get the same thing, please? Yeah, please tell me. S to the -1. Next. 0.20. Let's go to the next one. I want to be as fast as possible. Yep, excellent. We're doing well. Right. Ooh. Oh, guys, they've tilted the table. Yeah, you've got to be aware of this and watch out for this. It always takes me a while as well to fix it in my head. It's an absolute nightmare. Right, hang on a minute. Instead of comparing down like this, I'm now comparing horizontally. That's what I'm doing. So I want to work out the, there's only one person. That's nice. So from there to there, what have I done? Times by 2. That's a times by 2. What happened to there? It's going to be a times by 4, isn't it? Defo, 0.14 times 4 gives me 1.64. Amazing. So that is second order. I like it. Mr. Duncan, for equation 5, I could not see the data run as the power for the rate is fuzzy. What? Question 5. What? Mine looks okay. Have I made a mistake on, I don't know how it's gone fuzzy on yours, Winkit. Haven't got a clue. If you see the one you posted, I just downloaded the one I posted. Rate equals, K times by hi to the power of 2. Rate over hi to the power of 2. Come on. Gives me K. I thought the 5 minus were the same. That was why maybe you have to download. I don't know. Yeah, maybe you should have downloaded it. Don't worry, it's not a big deal. It's not a big deal. Did it actually come out? Did the numbers come out in the wash with that being out by a 10 to probably 10 to the out by a factor of 10? Don't know. Right, choose a data string. Yep. Choose a data string. Whatever. Initial rate. See, it's clever, isn't it? Choose a data string. It's very easy to stuff it up when they turn their table over. Rate is 0.41 over 1.64 to the power of 2 gives me K. 0.41 divided by 1.64 squared. And I get a K of 0.152 units. Moles per dm cubed down on the bottom twice. Yeah. So one of them cancels. 1 mole per dm cubed cancels. But then the other one remains. Bring it up. Moles to the -1, dm to the +3, s to the -1. Nice. If I don't like doing that. Just to show you that in action, we know that the units for rate are moles per dm cubed per second. We have the HI, which is moles per dm cubed, but it's squared. So we have to write it down twice. Cancel, cancel, bring it up. That's how I'm getting them. Just reminding you. Next. Can someone check me? Did I get the right answer? So you guys are going to get a different answer to me here on number 5. Just mental note. Download your worksheets. Yeah. Next. Right. We need 2 to stay the same. Stay same, stay same. 8 divided by 6 times by 1.33. What's that gone up by? 2.4. And they're to both 10 to the minuses, so I can ignore it. Goes up by 1.33. I like it. First order. Next. Rub it off in your exam. Right. Next, that one's done. Yeah, find another one where that one stays the same and that one doesn't. That's perfect. This is first order. That's a 1.33 again. Yeah, and then that's a times by 2. Step it. Right, that's going to become That is times 1.33 as a result of propanone. So 9 exponential minus 5 times by 1.33 gives me 1.197 times 10 to the minus 4. It's weird. It is 1.33, of course. And then that one there should have been a result of the same number. It's the same number. It's great. 0. So that's 0 order. No change. Like it. So we've picked up the second one. Right, now we get to the last one. Just need, the only way I can do this one is there. Right, they all change. So that's a divide by 1.33. That's a divide by 2. Right, step it, got to step it twice. Right, so divide by 1.33. Yeah, oh, I don't need to do it 3 times because it's 0 order. Yeah, so 1.2 exponential minus 4. Yeah, divided by 1.33 gets me 9.02 times 10 to the minus 5. Then it's going to go from there to there because this one's 0 order. It doesn't matter. So that must be, so what's the, that there, of course, is times by 2. And I'm pretty sure times 2 gets me the answer I'm looking for. Yeah, so it's first order. So rate equals K. H plus to the power of 1 and propanone to the power of 1 as well. Right, let's input my data, choose a string. Me. Love to know what difference it made if you actually left it as power of 4. A massive multiplier factor. Rate equals rate over H plus to the power of 1 and propanone to the power of 1 equals K. Input my data. Rate 2.4 times 10 to the minus 4, not 14. Oops. All over H plus. So I can ignore it. 1 times 8 is 8. So it's over 8. 2.4 exponential minus 4 divided by 8 gives me a K value of 3 times 10 to the minus 5. Units, moles per dm cubed, moles per dm. No, there's 2 of them down there. Ah, moles to the minus 1, dm to the plus 3, s to the minus 1. Did I get it right? For simpler H, I used experiments 15 and 17. It won't make any difference. But you did your 10 to the minus 4. Did you do 10 to the minus 4 and 10 to the minus 5? Because that's going to throw things way out. Isolate H plus only. Others don't change. Oh, yeah. Can. It shouldn't matter. We should get the same numbers. Shouldn't make any difference. Did everyone get the same numbers I did? First order, 0 order. K is 3 times 10 to the minus 5. Moles to the minus 1. dm to the 3s to the minus 1. Yeah, I don't mind how you do it. Doesn't make any difference to me as long as you know how to do it. Yup. Good job, Winkit. Thank you. Last one. Hydrolyzed, you will not be able to calculate K in this equation, in this question. Ah. Okay. So, relative. Okay, there's why we can't. Yeah, so can't calculate K due to relative. Yeah, they're comparing them to each other. They're not a real value. Yeah? Relative initial rates. Oh, units. dm to the 6. No. It's not dm to the, no, dm to the minus, dm to the plus 3. Yeah. Because they're relative, so we can't calculate it, but we can still look at their orders. Stays the same, times by 2. Ah, hang on a minute. Oh, moles of volume. Right. So the problem is we need concentration. Oh, but the volumes are only 1. So that is the same. The moles is the same as the if that was a different number, that'd be a whole different ball game. Ooh, the last one there is going to be tricky. Right. Which we've got to use. So because these are 1 liter, we can treat moles as moles per dm cubed. Yeah. Does everyone realize that? So that one I can actually just say times 2. Stays the same. What happens to the rate? Relatively times 2. So first order for him. Yeah, methyl ethanoate is first order. Right, this now becomes a problem. The reason being is the volume is half a liter and these are moles. We can't use them. We've got to convert these into concentration. And to go to concentration, number of moles is C times V, reorganize. Yeah, so divide the moles by the V, yeah, which is going to give me, it's essentially times by 2, times by 0.5. No, divided by. It's the same as times 2. Yeah, so my answer there, divide by vol. I made a mess. And I'm going to get 0.08 moles per dm cubed here. There's concentration. And that one again is going to be the same as times by 0.06 concentration. Now we can use it. It's a trap. But for question 5, there are 5 different concentrations. Yes, but one of them is 0 order, Dixon. So, okay, what did we do here? That was a times by 2. And we know that's first order, which means the original rate would have gone to 4 as a result of that guy. Yeah, times by 2. So that one there is a times by 3. What did I do there? Times by 3. It's also first order. No! Uh-oh. Oh, yeah, because I'm comparing it to the one above it. Yeah, there you go. Times by 3. Yep. That's correct. So that one's also first order. So rate equation, which we can still produce, K, ethyl ethanoate to the power 1, OH minus to the power 1. We're done. Can't work out K though, because it's relative. I see. Yep, got that. Cool. Clever trick. That last one was real, a bit more A-level-ish, a bit more A2-ish. Yeah, they've done all kinds of horrible games like that. It's proper horrible. So just be aware. Okay, brings us to the end of the homeworks. Right, I don't have very long left, annoyingly. Got about half an hour left. Good. Right, so our learning objectives. Mechanisms affect rate equations, RDS. Use of rate equation to predict RDS. Okay, so what we now need to do, guys, is we now need to talk about mechanisms. I'm going to switch to black. Okay, so mechanisms and RDS. So the first thing I need to do is I need to translate RDS for you guys. Yeah, by the way, the paper was out of, hang on a minute, just for the marks on the thing, you're going to have 1 mark for the orders. 1 mark for the orders for each question. So hang on. 1 mark for the orders. 1 mark for the rate equation. 1 mark for K. 1 mark for its units. Think so. 4 marks for each one. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. But this one you can't. You need orders and rate equation. You can't calculate K or its unit. You can actually predict its units you can calculate. Yeah, those you can still do. But whatever. I'm just leaving it at 2 there. So 4, 8, 12, 16, 22. It's out of 22, I believe. Don't know. Fill in the sheets there. Anyway, moving on. Mechanisms and RDS. So the first thing we need to talk about is what RDS stands for. Yeah. So, hang on a minute. I shouldn't really do that. Let's talk about mechanism. So, in chemical reactions, brackets, especially organic, there are often multiple steps in the reaction. Multiple steps in the reaction. Let's look at an example of this. Yeah, so e.g., yeah, let's do chloromethane. Let's do chloromethane with ammonia. Right. Year 13. Number 1, name the mechanism. Name the mechanism. And how many steps? I'm hoping that you guys are going to realize why I've picked it. I mean, I have literally had to think about it, pick the one that I wanted. Right, mechanism. So the mechanism is nucleophilic substitution. Uh-oh, this is nuke sub. Yeah. However, this is an unusual nuke sub as it's 2 steps. It's 2 steps. So step 1, find your delta. Step 2, yeah, find your nucleophile and its electrons. Shouldn't do that. It's a terrible curly arrow. Going to reorganize this. Yeah. Got to make sure that we're doing these things. We're kind of preparing everybody. My pen is starting to hiccup. There we go. And then breaks off. Don't ask me why my pen is being stupid. Next, it's 2 steps because I'm going to form this intermediate. All bonds now must be shown. Yeah, if you don't show your bonds, you'll lose one. And that's now N plus. Circled. Second step, another ammonia comes along and acts as a base. Yeah, and that rolls back. And we're done. So this is nucleophilic substitution with ammonia. We have formed an amine. Yeah, methanamine. That's what we've formed. Yeah, and we've also formed as a byproduct ammonium chloride as a byproduct. The reason being is in this step here, we see the formation of ammonium. Yeah, and of course, this is ionic. Yeah, that forms ammonium in that step. The chlorine broke away in this step. Yeah, this is where the chlorine broke away. Yeah, and they're just going to be floating around in solution together, but the byproduct is ammonium chloride. Yeah, and it's 2 steps. Now, what this means is if there's 2 steps, this is very similar to going on a car journey with 2 separate stages. Everyone would agree with me if I say this. If you go on a journey in a car with your parents or with your friends or whatever, and you've got to break the journey in half. No matter how hard you try, no 2 stages, nota bene, no 2 steps would have the same rate. You know, if you were going to go, it doesn't matter how hard you try, yeah, even if you leave at exactly the right time, you're never, because of the way that the inevitability of traffic, you never have the 2 journeys being exactly the same time to the second. It's impossible. What that means is, as a result, no 2 steps have the same rate. As a result, there will be a slowest. There will be a slowest step. Yeah, because of the inevitability, if I had a reaction, let's keep it simple. If I'm going to transform, this is where I start giving you guys bizarre equations. If I said 2A's plus B plus C gives me 3D's, yeah, this is my overall reaction. Yeah, my overall reaction. But what we realize is that this isn't happening in a single go. What's happening is 1A is reacting with a B to form D, yeah, and then, to form E, and E is reacting with another A to form a D plus an F, and F is then reacting with a C to form D, and that's it. So this is a 3-step reaction. It's a 3-stepper. 2 Ds. That forms me 2 Ds. Yeah. And what we realize is that this overall equation, by the way, do not expect, I'm just making this up. I'm just wanting to show you a couple of things from chemistry here, which is to do with equations. What we realize is that this is the overall equation, and these are the three steps that produce the overall. Well, let's just do a little bit of fun combining equations. Yeah, we can say that A and B goes to E, but then E is reused. That's an intermediate, and it came out on one and then used up in another. So that vanishes. Yeah, the F has been created now and then used up in that one. Yeah, and so what we can now do is add all these equations together. Yeah, we now get 2 A's on the left plus 1 B plus 1 C, and I've got 3 D's coming out. It gives me the overall. So we know that reactions, this is where my laptop is driving. I don't know whether or not it's my pen that's creating the issues I've got here now. Yeah, we realize that these 3 steps all add up to the overall. But because there's 3 steps, we know that they're all going to be different rates. Yeah. And there's actually only one step we care about in kinetics, and that is the slowest. So if I've got 3 steps here, and this is fast, and this is very fast, and this is slow, the only one I care about is the last one. Because what that means is that the first one is fast, but everything's going to compile. Everything's going to back up until you get to that 3rd step. Once you get to that 3rd step, everything's going to slow down, because it doesn't really matter what I'm doing with A and B, the first 2 steps, because they've already happened, and we're just waiting for the 3rd one to occur. And this here we now call the rate determining. This is where I need to make my pen thicker. And goes into this is an important thing. Rate determining step. Oh, my laptop is really, really struggling. It needs to be restarted. It's driving. Look at that. I'm using my rubber and it just doesn't work. So rate determining step. Uh-oh. Oh, it's done this again. It's done this again. Rate determining step. I think I might have just figured something. My Wi-Fi is really struggling too. Yeah, it's just my laptop's struggling with all the stuff going on. Rate determining step. The slowest step in a reaction. Okay, so now that we understand, so we can now flag this here. This is going to be therefore RDS. It is rate determining. Now we've been talking about rates. Yeah, we've been talking about rates. And I think what everyone here probably realizes is that if step 1, let's call this S1, S2, and S3. I think everyone here would agree, if S1 and 2 are fast and 3 is slow, if I add loads of A, is it going to matter? Is it going to make any difference to the rate? Just think about that for a minute. Would it? I've got a fast, a very fast, and a slow. We add loads of A. A is needed in the 2nd step as well, but it's not needed in the latter. So what I'm trying to get at here, folks, is that actually, by the way, A does matter, just so you know. A does matter. But in reality, what we then realize is, due to there being all these steps, the rate equation, rate equals K, X, W, yeah? This rate equation has a link to RDS, because we realize that some molecules just don't matter. Yeah, some molecules just don't matter. For example, E just isn't going to matter. E is produced in the first step and destroyed in the latter. Yeah, it's just not going to make any difference. An intermediate. Now, that doesn't mean that no intermediates really matter, but it's nice to be able to point out that you can often start assigning people these RDS points and rate equation kind of importance. And what we realize is that the rate equation can be used. This is the note. RDS can be identified using rate equation. Let me show you what I mean. Okay. E.g. Right. Example. So let's say we've got, let's start easy and get harder. A plus B goes to C. C plus D goes to E. Okay. Two-step reaction. Yeah, two-step. This is step 1. This is step 2. And here is my rate equation. Rate equals, okay, A to the power of 1 and B to the power of 1 as well. That's it. So which step is therefore RDS? On the chat, please. Which step is RDS? Which step is RDS, folks? Don't overthink it. Thanks, Dixon. Thanks, Winkit. Spot on. Of course it is. The answer is step number 1. Of course it is. What we see over here is that I have, a note. So hang on a minute. This here tells us that that's my RDS. Yeah, RDS. That's now what it does. And why does it do that? It does that because the reactants in the rate equation, are in the same ratio, as step 1. Yeah. So there is, and let's now do this in color coding. Yeah, there is 1A. It matches the stoichiometric ratios. Yeah, 1 and 1. That's where it comes from. Now, that is the most basic form of identification of RDS using the rate equation. Let's get them slightly harder. Let's do EG2. Okay, EG2. I'm going to have A plus B goes to, do you know what? I shouldn't do the same letters because it doesn't half get confusing if I do that. X plus Y goes to Z. Z plus X goes to W. Two steps. Right, step 1. Yeah, step 1, step 2. Rate equation. Rate equals K, X to the power of 2 and Y to the power of 1. Which step is RDS? Yeah, which step is RDS? Is it step 1 or step 2, and why? The hilarious thing is you pretty much Because the fact that I'm ruining all these pen tips. I need to buy myself a new Step 2 is the right answer, Winkit. Thank you. It is the correct answer. And the answer is exactly the same as the previous one. X and Y are in the... Nah, Dixon, you've fallen into their trap. The rate equation says... What this says to me is I need... in RDS ... what I need for RDS is I need in RDS I need, do it in order, 2 X's and 1 Y. That's what I need. Because these are to the powers in the RDS. X affecting rate without effect of Y? Yeah. No, you just need to talk about the ratios. Now, the reason why this is a trap is because people go, I have no equation where there's 2 X's and a Y. Yeah? And the answer is you do. It's step number 2. Because what was Z? Z is 1 X and 1 Y. It's a proper trap. Yeah? Z is an X and a Y. So we could say that because we know that these two become Z, we could pretty much swap that for X plus Y, which means I've got 2 X's and a Y. There's step 2. It's a clever trick. Yeah? So RDS is step 2 because the ratios of the reactants are in the same ratio as found in the rate equation. The same answer. Yeah? Let's look at another one. Let's look at a real one. And at this point, with 15 minutes to go, guys, I did not teach you guys organic, did I? I didn't teach you guys organic. Oh, did I? Did I do nuke sub with you guys? I can't remember. But the problem is nucleophilic substitution is now going to take a bit of an increase in difficulty. There are 2 types of nuke sub, SN1 and SN2. So just to show you guys this. So this is organic mechanism, nucleophilic sub. And there are now 2. There is SN1 and SN2. And this stands for nucleophilic substitution, 1 species in the rate determining step. This one is nucleophilic substitution with 2 species in the rate determining step. Just to quickly show you these now. So if I have a tertiary haloalkane, let's go for this one. So we all know that if you have a tertiary haloalkane, they actually react quicker, which is rather interesting. It shouldn't react quicker, but they do. Yeah, what's going to happen is this delta is so massively reduced. It's so tiny now that the OH minus ion just can't see it. Yeah, it just can't see it. It's not polar enough. Yeah, it just wanders around. What that means is that it becomes 2 steps. The first step in this one, is, I'm actually going to make this a little bit easier. It just looks so messy today. I don't quite know why, actually. Just going to make it a bit cleaner. Easier to see. Still tertiary. So what now happens is you go through thermal decomposition to produce this. There we go. Now in the second step goes the attack. 2 steps. Here's my question for you. Which one of these steps, and you're going to probably find this rather odd, which one of these steps was fast? If you need I can simplify this down if you prefer. Should always circle your charges. Which one of these 2 steps is going to be really fast? Winkit, you think step 1 is going to be fast? Step 2. Well done, Winkit. Well done. What Winkit has noticed is that if I just simplify this as A plus B goes to C, and then if I then did compared to, let's do a versus game. Yeah, versus A plus B minus going to C. Which one of those 2 reactions is going to be fast? And the answer is the latter. Yeah, the answer is the latter. This one here is going to be really fast. This one, really fast. Because opposite charges attract. This one is going to be much slower. Because there's no attraction. They've just got to collide randomly. This is an attraction. Yeah, attraction versus random. Yeah, versus random collision. Yeah. So step 1, you realize the reactant is uncharged. That's got to fall apart. But in the second step, we've got fully charged ions. This second step is going to be quick. So the rate equation for this, 2 steps, the rate equation for this process, yeah, is rate equals K. And I'm just going to, I really wish I could just, the tertiary haloalkane. It's the only thing that matters. The sodium hydroxide doesn't matter because the second step is so quick. That's it. And it's to the power of 1 because there's 1 in it. Isn't that clever? The order matches the ratio in RDS. Right, that brings me to the end of my lesson. Whoop, whoop. Right, guys. Okay. You 3, I will set the homework right now. You've got RDSs to locate using rate equations. I will see you guys after the long weekend. Have a nice long weekend, guys. See you soon. You're very welcome. It's a pleasure to teach you guys, as always.